Very much, Martina. It's my great pleasure to introduce right away our first speaker, David Navarro-Alarcon, and he's a professor at the Department of Mechanical Engineering at the Hong Kong University Polytechnica and the principal investigator of the Robotics and Machine Intelligence Laboratory. He received his PhD in Mechanical and Automotion Engineering from the Chinese University of Hong Kong in 2014, and his current research interests include perceptual robotics and control theory. And I'm very happy to welcome him here. And yeah, take it away, David.
Thanks, Michael. Thanks, Martina. And thanks to the other 11 workshop organizers. Is that a record? Possibly.
Yeah. Probably.
Yeah. Anyway, so let's start sharing my slides. So I trust you guys didn't change any special Zoom settings so that I can use it.
You can trust us.
Yeah, but if it doesn't work, I will easily blame you. So
that's good that it works.
Okay, so yeah, I guess I begin. So thanks a lot to the 13 organizers of this workshop. You know, kudos to you guys. It's a very fashionable topic nowadays. So, well, here the presentation I'm giving is mostly of the work that I've been. Actually, mostly it's all about the work I've been doing with my group for the past 5 to 6 years. So I mostly work on manipulation, sensor-based manipulation. So for some reason, I'm only asked to talk about manipulation of sub-objects. Probably in a few years, I hope I can be asked to share my work in these other areas. But in this talk, I will share the great majority of the work that we have related to sub-object manipulation. So yeah, as I and all the others that will present today, we know and we all claim and make strong emphasis on the necessity to study this problem. More than the necessity, my intention with this slide is what is the difficulty? I mean, for someone, we have like 50 something speakers. So, someone who probably hadn't worked on this problem before, they may wonder, is there any significant difference in manipulating something that is rigid or something that is soft? Say rigid, we have basically many objects. Soft, I was thinking this morning actually about, is it fair to say that the great majority of the objects we have in common environments are non-rigid? I don't know. Probably for discussion if someone may elaborate on this issue. But what they represent the great majority is a capability that we want robots to be able to autonomously perform the manipulation of these materials. So the difference between manipulating these two, whether being with a robotic hand or several manipulators, is that for a rigid object, its configuration, so now let's go technical, its configuration, its feedback representation is fixed. So we have at most 6 degrees of freedom. We have 3 of position, 3 of orientation. Now, how does this situation changes with deformable objects when manipulated by an object? How many degrees of freedom, how many coordinates in a feedback vector do we need? Well, in principle, theoretically, we know that deformable objects, they have infinite degrees of freedom. And this is precisely the central theme in the talk that I will give today. How many coordinates do we need to perform what I call in the work that I do a shape servoing task? So this is the underlying question of the work that I have today. So yeah, soft-object manipulation is the fashionable topic nowadays, isn't it? We have reviews every 6 months, a new one. We have special issues. We have workshops. We have probably in a few months a podcast about this topic. There's a lot of people working on this, and don't see this as a criticism. I'm posting this, trying to highlight the importance of this area, because manipulation of deformable objects, providing these capabilities to a machine, it really has many applications in so many. I really don't want to spend too much in motivating saying that this is important, because being here and giving a talk in a workshop should already be implicit such a necessity. So the work that I'm showing today is about a problem that I call, I don't know, can I even say that this has entered the state of the art? Can we use the term shape servoing? I don't know, well, at least I am using this term. So by shape servoing, we, well, if I put it in say in terms of areas, we know there's an area called visual servoing where say you have a camera, you have a manipulator, and you generally regulate some features. You want to minimize an error. So shape servoing is the natural extension to that problem. It is a control problem, but to control the extension to controlling instead of like a feature of I don't know, let's say a square that you're observing with a camera. What we are here trying to, on one hand, characterize, and on the other one, deform is the shape or the configuration of a manipulated material. So I have a pen actually. Let's make use of our didactic tools that we have acquired in these months of online teaching. So does it work? Yeah, it does. All right. So we can, in a graphical way, describe this shape servoing. We have let's assume we can measure somehow the feedback shape of an object. And this is a target shape. Let's say we want to bend it. So in a very simple way to define these problems, we want to design a trajectory of the robot that minimizes this very standard quadratic error. So nothing special here. Well, I don't know, there's a question here. All right. So let me move this one. Yeah, so yeah, this is the main topic that I'm presenting today. How should we represent such feedback configuration of the object? So as I mentioned, in soft bodies, from a materials point of view, they have infinite dimensional, infinite number of degrees of freedom. So when we model this manipulation problem as a control problem, we have the necessity to compute this feedback shape of an object. So one of the questions we can start asking is, so how accurate or how detailed such representation needs to be? And this is a very crucial factor, because depending on the level of detail that you want will be the size or the dimension of such representation. So, there are many ways. I don't think there's a unique way to do it. And this is an actively studied problem in this field. So we can see in this figure, these are all screenshots from papers and experiments we have done through the years. So we can represent perhaps shape with angles, as we will show later on some experiments. We can represent them with simple points, such as this one. We can represent them with some contours. We can represent them with points in 3D. And anyway, there's really many ways you can do it. Now I start here drawing some attention to an important issue that I think, if we are to give you some hints and some clues from the experience that we have acquired here, is there's an approach that I call here the naive approach to shape servoing. So again, this is a control problem. I here very much emphasize that simulation, numerical simulation, virtual reality simulation, finite element model simulation is the objectives of such a field. They are different, or generally different, from those of control. So we cannot equate simulation to control. So for example, if we have various cases where we may be able to manipulate, say, something in 3D to observe. First of all, we can observe, let's say that we are observing this object, some foam sheet with a point cloud sensor. So these are some typical, shapes, surfaces that we might be able to compute. Let's assume for some moment that, this is what we want. We want the robot to deform this one into this one. So the question here, and as the talk that I'm giving tries to pose and partly solve, how should we characterize the shape of this object so that we can use it in a control scheme? So if we just use this approach that I call the naive approach and just take entirely the raw dense feedback from a point cloud sensor, we may have like way too many coordinates. I mean, this is just an estimate, let's say 600 numbers just to represent, you know, this surface. In this other case, how do I move this thing? In this other case where we can observe, for example, a cable, very active, also many people working on this, we might be able to, you know, add a very high contrast background and observe a binary image of that cable. So if you compute or extract the contour to all that binary image, how many numbers do you think you can get? I mean, also very rough estimate, say, well, we can easily get 100. So are these two representations suitable to define this vector suitable to, one, represent, and two, control the shape of deformable material? That I can, well, fairly say that probably not. I mean, it has way too much information that what we actually need to do this problem. So if we represent it as a series of steps, so the I'm deliberatively using the word latent because it's although in the field one may associate latent with almost exclusively with a network. We can generalize this concept as, let's call it the non-evident way to represent the configuration of a sub-object. So I'm here calling that we have some shape encoding algorithm or method that will, from it, we will extract a series of numbers that can fairly characterize, maybe even almost locally, quite globally, the configuration of this object. So our interest in this talk is to find different ways to compute this one. And how do we use it in, well, this is a very also standard a feedback control problem. We have some plant, we can feed the shape back and we can define some target. So we will be giving you some examples of the work we've been doing specifically on this one. Okay, so what is the, well, I would call this the trivial solution to do is if we can use some specific geometric features to compute, let's call it centroids, angles, distances, curvatures, and its combinations. So any non-geometric function based on some point features that you may be able to detect in the surface of your object. So we can use such functions, say, for example, let's say a centroid or an angle, to characterize the configuration, the observable configuration of this object. So we did this in probably too many papers. I mean, it's a very, I would call it the very trivial, because it's the direct extension of what one from the visual servoing community would do. So, I mean, this is like really the natural way you end up doing it, because it's the easiest way to do it and closely resembles the visual servoing problem. So, but it has some issues. The type of shapes or configurations that you can encode by using hard-coded geometric features are very basic, very, very limited. And once you define it as such, you cannot morph them into something else. So once you, let's say, coded curvatures and you want to do something else, then that's it. I mean, your function cannot change. And that brings several limitations to the problem. So we can, of course, define more general approaches, and these are not as specific for some geometry. Let's say, for example, bending. That's very clear, like practically. Once you coded bending, you can't really do it stretching somehow. So we start studying like more general approaches to represent, in this case, contours. So we use, very also, it's very standard way to do it. So we use Fourier series, like finite number Fourier series to approximate the observable contour of an object. So the reason why we did this is, well, from a control background, we can then use very well-known tricks that we use everywhere. So we can split such approximation based on like a known regression matrix that you can measure based on sensor feedback. And then you have here a vector, which are here the so-called Fourier coefficients. So it turns out that these coefficients, we can, that's our proposition here. We use the coefficients as, I don't know, let's call it as a proxy to shape. It's not shape per se, but they can encode a shape that you're observing with your camera with a locally unique set of vectors. So here again, I highlight this has to be with using finite Fourier series, because we know that from the theory, the infinite Fourier series, well, it will exactly approximate everything, but it will give you a gigantic vector of coefficients. So if we put it as a pipeline, what is quite simple. So we binarize the image, we compute the arc length, we use observations of data along the arc of your shape, and then we can just use least squares estimation to compute such vector. Compared to the approach that I call the naive, how much could we reduce the computation? Say we had from a 2D image, like a 200 so vector, we end up having, say, for example, if we use 4 harmonics, we have 18 numbers, so from 200 to 18. So, you know, that's quite something. So how do we use this representation for control? That's also a central theme in what I do. So it's, well, we also, I don't know, if somebody's expecting very advanced theory, it probably is not the right talk. I use also very standard methods. So I use a very conventional Jacobian-based method to project. First of all, you have a contour, desired contour, you project it into Fourier coefficients, desired Fourier coefficients, and then you project this differential. This is actually a differential in shape space. You project it now into robot motions. You know, that's what we generally do with sensor-based control. Key here, as someone may wonder, is how do you compute the Jacobian metrics? There's so many recipes, and I literally call it like that, recipe, because you just use it to estimate a Jacobian matrix. So let's see some results. So, well, here we're using 2D motions, and the sensor also gives us 2D shapes. Well, things to highlight here is, well, what we are doing is we are encoding a high-dimensional observable shape from an object just with a few parameters. In this case, depending on the number of harmonics. I don't remember, I think this experiment I used 3 to 4. I use less than 20 parameters, so it's not so detailed. So as you can see, what we do is we remove all the high frequency information, you know, all the little details, which even if you have them, that's a question, does it help from a control point of view? What would you do? I mean, if you hadn't really reached that specific detail, can you still control it with limited number of grasping points? Not really. So that's one of the reasoning that I put as for not using the dense measurement of the object shape. Well, we naturally extended this idea to, well, there are many analytical formulations of say curves. So we have from the graphics field, we have what we call NURBS and Bezier curves. So we use these other representations, and we literally follow the same set of steps that I presented before, observing a contour, characterizing it in terms of its arc length, and then we can use least squares estimation to obtain not Fourier coefficients, but we will obtain different coefficients. Let's call it like NURBS coefficients and also Bezier coefficients. So these are numbers that locally they help to characterize the shape of an object, in which we can use as a quasi-feedback signal for control, for deforming this, well, it's a cable, in this case, to a desired shape. So, oh, actually, here it is. You see the green little dots? Way too many, multiplied by 2 for a camera. So it's a very long vector. In this case, we don't need that many information. You know, let me try to remember how many. Same case, I don't think we use more than 20 numbers to characterize these curves. we also work, this is some work we work with Montpellier, also a natural extension of all this is to use, this one really brings the concept of optimality in the sense of really orthogonalizing different notions of and properties of shapes. So we use PCA tools to do the eigen decomposition of a series of observations. So let's here briefly review what we do. So let's say that we collect several, in the paper we actually did local observations, but let's say that we collect a whole global set of contours of the object, and then we construct, let's call this the data matrix, observation matrix, and we just, I think this one is like median probably. To these we can eigen decompose it and then obtain the matrix, this matrix U, which contains the eigenvectors. If we select, the power of this is that it will tell you how many coordinates you actually need to represent to a desired degree of accuracy. So it's going to completely orthogonalize the, let's say, the specific properties of the shape in the object. And by selecting, a given number of eigenvectors, we can then project. So everything here means feedback. This is your contour, your feedback. You simply project it with a selected number of eigenvectors to reduce space. In this case, obtained from such PCA-based decomposition of shapes. We will use this with exactly the same in the previous servoing approach for doing control. We are going to use this as a quasi-feedback signal, and we will design desired features that relate to this same PCA-based representation. So with Andrea Carvini and Ji-Hong Zhu, we conducted several experiments. These are 2D cables, similar to the ones we did before, but using different theory. The standard now, spongy being deformed into a desired contour. One important aspect here is that with exactly the same method, for the method's point of view, the representation, it doesn't really matter if it's a rigid object, a soft object, a mixed properties object. We're just characterizing its configuration. So we use it to do both deformable, shape, to do translations, translation plus deformations, and so on. So, we have more details in this just recently published paper. And also if someone says, well, these guys use PCA, why don't we use, the autoencoder? It's also very similar, related. So how would we use autoencoder for doing a representation of this? So, exactly as the autoencoder works. So we will have a set of contours that we will use to train this autoencoding network, and we will use in this case the bottleneck layer as the shape coordinates, as the latent variables the quasi-feedback variables that we will use for control. So in contrast with autoencoder and all the previous one, it also doesn't necessarily provide you orthogonal latent coordinates. So it will just give you some numbers. And you may also have in its standard form, the question of how many coordinates do you actually need to represent that, to represent it well. We don't really, at least in here, address that problem. We use also PCA as a guide to select the number of codes. What should we looking here? Also interesting. We have, we can obtain some semantic information here. So if we visualize this in the reduced space of the, this is for 3D, by the way, of the 3D contour, we can find some information as to what kind of shape the object has, and we are sensing. For example, we can have a helix, we can have a positive arch, negative arch, and so on. So this information might be given by PCA if we run it in parallel. Which also leads us to the issue of we have actually for for this work been just simply designing controllers where we want to drive the feedback to a desired location. With a student of mine, Jeffrey, we recently started developing a method that we model that, or this is the formulation we have, that these latent variables that we use, for example, from an autoencoder, or literally any of the other ones, that is not necessarily restricted to that specific neural network architecture. Fourier and the others might produce the same, that locally small changes in the robot pose will produce small changes in the shape. So locally, this will resemble a Euclidean space, but if you see it as a globally, some trajectory might not be a connected one in the shape space, as for example, here we are describing. So what we did is we constructed such manifold and then start designing trajectories, which are like geodesic trajectories over such manifold, in order to avoid, say, what it could potentially be unfeasible shapes. And in this paper, we also found that by simply doing the linear interpolation, we might find some, linear interpolation in this space. So it might be some shapes that are not, there's not a sequence of shapes that are not really connected or physically achievable from one state into the other. Whereas if we work on developing, on computing the geodesic path, we can find a smoother set of shapes. So this is a nice, interesting planning shape problem that we have been recently working and just recently released in REL. What else do we have? Okay, yeah, this is also all very recent work. So I told you all about this talk is about different ways to represent it and using the control. The task remains the same. Yet another way to represent it is by using contour moments. So this is another work that we have been working with my student from HIT. So what do we do here? We have three main parts of this descriptor. We use standard contour moments, which we know they're invariant to translations and rotations. So with this first part, we have 7 numbers that describe in an invariant way the shape of any object. It doesn't matter whether it's deformable or not. We use central moments, like centroid, to describe the position, the translation of this object. And we use the orientation of the principal axis to describe the rotation on the plane. So in here, we can see how, say, for many collected, this is in simulation, many shapes, we can see how these descriptors are varying in its respective space. So we normalize all these because they all have different units. And here's just some experiments showing the same with different types of objects, cables, some spongy, and I believe even a rigid object. In this paper, what we are working on, this is a control paper, very control paper. We are comparing different types of controllers. So the one we're proposing is this one. We're proposing finite time sliding mode control. The other ones still work also quite well. I mean, it's a control. You need to highlight some issues. In this case, it's exact minimization of the error. But the interesting thing here that we are addressing in this paper is the notion that the same shape descriptor and control method can be used not only to soft objects, but also to do, to consider more like a spectrum, entirely going from purely elastic to rigid, and what we here addressing and call as composite. So we are proposing a method for deform or position composite rigid deformable objects with the same method. And these objects might have different types of properties. More from a practical aspect, this is the latest work of my student here in PolyU. We are working towards doing packing, optimal packing of precisely what we mentioned before, which might be some soft objects, rigid objects, composite, rigid deformable objects. So our idea is to design an algorithm, an optimal algorithm that can decide in an optimal way the type of box that you need to use for optimally packing a series of objects. So we are working on action planner for, at the present stage, we're mostly working with soft and deformable materials. But the idea is that we want to, for example, in this case, completely transfer all these objects into smaller box and decide its a specific location. So in this case, what we have been working is on the action planning point of view. So we are designing a series of grasping, re-grasping, and jointly deforming an object such that it fits the expected shape within a confined workspace. In this case, the box. I'm not taking time, but well, this is the last one. Okay, so conclusions for me talk. I have today modeled, as I do with this line of work, the soft object manipulation as a control problem, specifically as a servoing problem, where we can have some form of output representing shape, and then we just feed it back and have an explicit shape error. Key to do that, which is the main topic in this talk, is we can represent in many ways such shape with standard geometric features, Fourier coefficients, nerves, Bezier, principal components analysis, contour moments, and so on. There's probably many other. And by doing that, we're able to do automatic control of manipulating objects and deforming them in various shapes and configurations. So this is the end of my talk, and I thank you all for inviting me. And I'm not sure if I still have time to answer any question.
Thank you, David. Yeah, I think we have some minutes, and we also got some questions. We have the first question from Martin Sundermeyer in the Q&A system of Zoom. In case you want to read it yourself, but it says, wouldn't dense non-rigid registration be required in order to distinguish between object pose changes and object deformations? I.e., are sparse 2D representation like contours not too ambiguous in that regard?
Is it valid to say? I don't know. No, well, I refer back to the too ambiguous. No, actually. Yeah, I think I get, say, what if, say, I don't know if I'm reading the question correct, but let's say, oh, I can draw. Yes. Let me draw. These things do help. So let's say that we have this shape and it has a small, I don't know, high frequency analysis. That looks like an angry bird. Okay, let's say we have an angry bird, all right? And if I use, very few harmonics, let's say we're using Fourier, we might be able just to remove, the nose. How do we really deform it or rotate it into the way that we want? Is that probably what the question was about? No, yeah, actually, this is a valid point. I do take it. It's true. I might revise my slides based on that later on to say that we don't need it. I say we might need it for these cases.
Okay, thanks. We have another question from the Slido from Rachel Holiday. Could you discuss the pros cons of your virus representations in comparison to each other? Why choose one representation over the other?
Yeah, well, at least in papers, I deliberatively avoid doing that. But no, yes, it's from a reviewer point of view also very good question. Well, if we, can I go to the previous one? I personally like, for what it provides and what it offers, I like principal components analysis. It's so clean and elegant in a way that you can really talk about optimizing. If you go to, say, Fourier, Bezier, contour moments, very frequency and repetitive, but not in an optimal way. PCA does give you a minimalistic way to represent everything. So I mean, my take will be that in that sense, if we consider all these properties, PCA is superior to those.
Okay, thanks. I think we have time for one more. Anonymous wants to know how you found the desired contours in the first place for the shape serving.
Oh, well, the truth in the experiments. Well, I mean, how do we find it? You can actually draw it yourself. I mean, it can be literally any contour. You can, I don't know, it can be the angry bird that I just draw. I mean, you can have anything, and from here you just extract that vector of parameters. In the experiments, in order to know whether it's a nearby feasible contour, what we did is we deformed, say, the object towards some region. We collected, save, that observation of shape features and just move elsewhere and then try to go back there. That was the experimental approach, but that doesn't mean that the method is limited to that. That was just simplicity for the person doing the experiments. You can draw anything, and an algorithm should be able to extract the numbers that represent that.
Thanks. And I think we have just one more question, so I'm going to also ask it. Faye asks that it's kind of a sensible approach for 2D contour representations, but what's in a 3D case? It happens that different 3D shapes can project into the same contour in image frame. What will happen in this case, and how to handle this?
Yeah, no, yes, it's a valid question, actually. But, well, I mean, look at this. I mean, this slide. So you can have, say, let's say if I go with my favorite PCA, you may compute your PCA for, I always have it with me in case somebody asks, of a 3D object like this, no problem. Given that you have the necessary observations to know the shape and the configuration that you have. Say, for example, where was it? In this one, actually, we don't see here very clear, but my student, she's actually computing the backbone of this object. It mostly moves in the plane, but that's by design. I mean, we can also move it in 3D, and we should be able to observe it. So no, it's actually not restricted to 2D. Experiments and many things, we've done it in 2D, but analytically, there's no way why it shouldn't be feasible. And actually, well, some of the results we saw, I didn't emphasize this, some of those are actually 3D. We did show something with geometric features. We do have something with Bezier. Also, these contour moments we have done in 3D. So it's feasible, yeah, and has been done.
Thank you so much. This was really a great talk.
Right.
And yeah, thanks you again. And we're handing it off to Martina to introduce the next speaker. And have a good day, David. And we see you in the first discussion round, if I'm not mistaken.
All right. Cheers.
All right.
Thanks, David.